In this video, we'll be discussing interpreting computer output from a different system than R. We'll also discuss a bit about how we can check some of those assumptions we discussed, though we're not going to talk too much about how to fix them. So I'm going to kind of leave you hanging, encourage you to jump into an additional stats class if you're interested on that. There's a ton of solutions available. None of these problems that we'll see or consider are anything new, and in fact, some we'll talk about in the multiple regression chapter. But we should discuss how to check these assumptions because when they are wrong, our significance tests are wrong. Now, our parameter estimates, the point estimates, those best guesses, those are going to be right for fitting a line. Now, sometimes a line is not the best thing to fit, but those are still going to be right for the best line according to the least squares definition of best. What's going to change is that t distribution and those standard errors. Well, specifically that t distribution. That's going to be the big one that if we no longer have like a normal distribution or homogeneity of variance or some of those things, that's what's going to be wrong, and that can lead to some inappropriate confidence intervals and inappropriate significance tests. So pretty much we can't do anything inferential. That is, no confidence intervals, no significance tests if our assumptions aren't met. Okay, so for the computer solution, now there's some Excel stuff. I know your textbook talks about that. I don't really like Excel for this. I shouldn't say that. No, I should. I don't really like Excel for this. Other professors do. You're welcome to go check with them if you want more stuff. And again, our textbook does. I'm not bashing Excel. It's just not my preferred tool. So Excel, one nice thing is that you can get some add-ons for Excel, and there's a regression add-on that you can use for Excel. And this can be used for doing a regression. In fact, again, my bash on Excel isn't that it can't do the stuff. I think you can do almost anything in Excel if you have the time and patience to put it in. And some of these pre-made tools give Excel a lot of the same abilities that any other stats software has. I just prefer to use something that's a little bit more comprehensive like R personally. In fact, I just had a meeting with the vice president of a bank. Well, it was today, my time. I don't know when you're going to be watching this video, but and the banker was saying that in her master's degree, she was working on a project that involved R, and one of her big regrets is that she didn't learn more about R at the time because she uses it all the time and is looking to hire people that know it. So if you're considering going for a bank or taking some of your skills into that world, consider that there's at least one vice president of a bank that's really looking for people that have that skill, and there's probably more. It's definitely something to advertise. This said, I like R, but it is important to be able to read output from a whole ton of different computer programs. So your textbook slides had some Minitab output on here. I left this in because I thought it would be a good thing for us to discuss and look at. So let's take a gander at this Minitab output and try to read it and pull out the pieces. So recall our independent variable is the TV ads, and the dependent variable is the number of cars sold. So in this output, I see that I've got the regression equation up here. So this is a kind of nice way to write the regression equation. I do kind of like this. And in my upper level classes, sometimes I encourage students to replace X and Y with like a short description of what they're talking about. So X is the TV ads, Y is the cars, and that's kind of nice. So for the predictors, constant, you'll see this in a bunch of different types of output. The predictor column label isn't always there, but constant or intercept usually is. This is our B0. And then adds, what's interesting here is instead of slope, they write the variable name. And this is because sometimes you will have multiple variables and you need to be able to keep all the different slopes separate. And if they just wrote slope 1, slope 2, slope 3, that'd be confusing. So what's clearer is to just write the variable name. And for you to know, this is the slope for that variable. So in adds, my independent variable, the slope is 5. As adds goes up by 1, the outcome cars is expected to go up by 5. Got the standard error for each of these coefficients. I've got the t-statistics testing each of these and the p-values comparing each of these to 0. Now the p-value for the intercept is not often looked at unless you have a reason why you think the number of cars that you sold should be 0 or not when you didn't have any adds, but almost always we kind of just ignore that constant line. It's just there. What we do like to look at is this adds line, and we can see the p-value 0.019 indicates a statistically significant linear relationship between the number of adds we take out and the number of cars we sold. You can see I have r squared here. I've got an adjusted r squared that we'll talk about in the multiple regression section. And both of these are indicating a pretty high percentage of variation in the number of cars sold, explained by the number of adds we took out. This is indicating that adds is a pretty important variable. Now for the ANOVA table, this is going to tell us some very similar information, again, because the ANOVA table is used to test all of the variables in the model, and we've only got one independent variable in the model. The ANOVA table is going to be a lot of copying. Now note that the ANOVA table does have some unique information because it focuses on sums of squares instead of these parameter estimates for our model. So it's just looking at it slightly differently. The parameter estimates tend to be more useful when evaluating variable by variable, and these sums of squares breakdowns are useful when trying to look at the whole model. Again, we're doing a different thing with this table in the ANOVA than we are with the parameter estimates table. So here, what I have is I have the sums of squares, the mean squares, and then the F ratio. Now I can use the sum of squares, 100 divided by 114, to get this r squared value, remember. How much of the variability is from regression, how much of the variability is total, and then dividing those says how much of the total variability, what percentage is due to regression. That's what gives me the 0.877, or when I express that probability as a percentage, 87.7%. Looking at this F value, if I took the time to take t 4.63 squared, I would get this 21.43. Again, for simple linear regression, these are going to be related. T squared is F. And then you'll note that the p-value is identical between these. This should always be the case, that the slope p-value and the overall model p-value is the same. Recall that the reason that is because the slope p-value represents the contribution of the only independent variable in here. The intercept isn't an independent variable. The adds is the independent variable. And this tests the contribution of all of the independent variables in the model, so these should be the same when there's only one independent variable in the model. Now software is kind of nice because it can do the confidence interval and prediction interval estimates. Now note, I don't have the confidence interval for this coefficient listed in this output. We can get it if we wanted to, but it's not listed by default. However, I can get the confidence interval around the predicted value. So the predicted value I have is 25. I see the standard error for that predicted value is 1.45. And then I have my confidence interval and my prediction interval. Recall that the confidence interval is there for if I'm looking to tell what the mean of a group of different stores would be. So on average, how many cars would a group of stores sell? That's what my confidence interval is telling me for 3 adds. So the middle is 25 cars, but then a reasonable range of values could be anywhere between 20 and 30 for my group of stores to sell. My prediction interval is looking at an individual store. So if I looked at a single store, I would say that on average, for a single store, I'd sell anywhere between 16 and 34 cars for a single store. Again, this is going to be slightly more variable than the confidence interval because a single store can move up and down a lot more than the whole group would move up and down. So this goes a little bit over the Minitab output and what's there. Again, the biggest thing that we've talked about that's missing from there is the confidence interval for the slope coefficient, but you can pretty easily calculate this because you have the coefficient, you have the standard error, you don't have the critical value for t, so you just need to calculate the critical value, multiply that by the standard error, and then add and subtract that from the coefficient, and that would give you your confidence interval for the coefficient. Now, residual analysis is one way to say what I feel is maybe a little bit more complicated way to say checking the assumptions. Residual analysis is used because to check the assumptions, we look at the observed errors, which are called residuals. So we don't have, notice error is written in this epsilon. This is a population value. All the Greek letters are population values. We never know them. But error, so that's error. E represents the residual. This is the observed error term. So when I'm looking at figuring out if my assumptions about the errors are right, I look at the residuals, the observed errors, the difference between my predicted value y and my observed value y, or the difference between the line and how far off each of the dots are from the line. That's my residual. And I look at how far these things are off because I make assumptions about the way that these are distributed. I assumed they were normally distributed, I assumed they had equal variance, and so on. I think I mentioned previously in this lecture set that I prefer graphical methods. Now, there are statistical methods to assess the statistical assumptions, but for me, the statistical methods themselves make a fair amount of assumptions, and at certain sample sizes, they tend to break down pretty quickly. So graphical methods tend to be far more preferred than statistical methods for me personally, and to be fair, for many others in the field. So we're going to talk primarily about the graphical methods. This said, you absolutely can use statistical methods for these if you're interested in doing so. All right, so the first graphical method is called a residual plot. Typically, you have the residual on the y-axis, and for simple linear regression, you can have x on the x-axis, but more generally, we have the predicted value y on the x-axis. In fact, I'm going to write that and cross out x because I'll just put an x over x, whatever. You get what I'm saying. I prefer the predicted value of y on the x-axis. It doesn't particularly matter in simple linear regression. In multiple linear regression, this is a very important distinction. In simple linear regression, these are going to look almost identical to each other. So what we're looking for is just kind of a random distribution of values. So recall we have two assumptions that we tend to check. The first one is normality. And the second one I'm going to call HOV. This is a term from ANOVA. It stands for homogeneity of variance. In regression, the fancy way of saying that is homoskedasticity. But really what this says is that there's an equal distribution of the points around the line. That is, it doesn't go skinny and then get wider, or start wider and then get skinnier, or kind of get wider and then get skinnier again. That the points are relatively variably consistent around the line. So these are the two assumptions we're checking. We use the residual plot to check homogeneity of variance. So to check the equalness of the points being distributed around the line. We'll have a different plot for normality when we get there. So this is good. This says, all right, there's roughly an equal amount of points around the line. This first one is not particularly good. It's not particularly bad either, but you can see that it does get a little bit wider as you go from left to right, and so that's the problem, is we don't want it to get wider going from left to right. Again, other problem shapes might be getting narrower going left to right, or getting wider and then narrower going left to right. So these would be problems. Really, any pattern in these residuals that doesn't just look like random dots is a problem. This one, this non-constant variance, I'm not too worried about. I do see it, how your textbook could say, hey, this could be an issue. But honestly, in practice, this looks pretty good to me, to be quite frank with you. Ones I'd be worried about is where this is really, really clear. So if I got 30 more data points and they were all falling within these lines, or 100 more data points and they were all falling within these lines, that would concern me a lot more. Now, the second plot is not something we talked about in one of our assumptions, but you can see a curve in the residuals. So this curve in the residuals tells us that this data is not particularly linear, that the relationship between x and y maybe needs to have a curve component to it, and that the assumption of a linear relationship is not particularly good. So this isn't necessarily a written out assumption, but it is actually an assumption that we make. We do assume that the relationship is linear. So in this particular case, would check this. We'd say, okay, this is a problem, and we'd want to say, okay, well, what can we do to fix this particular problem? And in this, we'd add a curvature component. How do we fix non-constant variance? Again, this goes beyond the scope of this class, but real quick, if you're interested, you could check out things like transformations. Of course, you could also use a type of regression that doesn't assume constant variance. It's a little bit fancier. Okay, so doing this for our actual data set. So this was our, we had our different observations. We had the predicted number of cars sold. This is what our line was. And then we had how far off we were. So we were off by -1 for observation 1 and 2. We were, let's see, we had the observed minus the predicted. So this was 16 and this was actually 26. For observation 3, this was actually 22. So we were 2 off. And then for 4 and 5, it looks like we were 2 above. So this looks like maybe it was 13 and 23, or maybe these are the opposite directions. In any case, looking at this residual plot, I'm looking for a pattern above and below. What's interesting here is I don't really see much going on. Now you'll notice that with few data points, you're not going to see a lot of patterns, and this is very, very, very common in few data points. Could you say that maybe something non-linear is going on here? I guess maybe there's a U shape, but honestly, I don't really see it. Again, you got to have some tolerance. You got to realize that there's going to be some random fluctuations. There's going to be some random patterns. And if you look for something hard enough, you're probably going to see something. So it has to be really, really, really obvious such that it's screaming off the page for me to get pretty concerned about it. In this case, nothing looks really obvious screaming off the page to me personally. Now, one other thing we can do with some of these plots is we can construct what's called a standardized residual. Now, a standardized residual just uses that old standardized equation. Now, remember how we standardize a variable to make it on the standard normal distribution, x minus mu divided by sigma. Well, we don't have mu and sigma. We have the sample mean and the sample standard deviation, and we can definitely standardize values. Sometimes it's called studentize values using this equation. So here we have y minus the predicted y divided by the standard error of the error, which is pretty confusing, but the standard error of the residual. So in this particular case, we'd use this equation. It's pretty, it actually should look pretty familiar to the equation for the predicted value. So when we were coming up with the construction intervals, or excuse me, the confidence intervals and the prediction intervals for the predicted value, this standard error equation should look pretty similar to that. So this is going to be pretty similar, and we're going to do the value minus the mean divided by the standard error, just like so. And we're going to do this for all of the different points. Now, the reason that we do this is because we don't want to have any crazy big errors. If we see any really, really large errors, that can be a problem. The issue is, how do you tell what is a quote unquote large error? Well, if I put it on this standardized scale, I can use the standardized interpretation of like a Z to tell me what's big and what's small. And typically on a Z scale, between -1 and 1 is pretty like normal. -1.5 and +1.5 is starting to get, I don't know, that's probably pretty normal. It's pretty fine too, pretty regular, nothing out of the ordinary. To be between like -2 and +2, like 1.5 to 2 and -1.5 to -2, things start to get a little concerning, and then outside of ±2, we might start to get concerned. So here I've got my residuals. I go through that process, the residual minus the predicted value divided by that standard error, and I get these standardized residuals here. And then I can plot these on the graph. So here the textbook is indicating that -1.5 and +1.5. We don't see anything outside of that range. There's no reason to question anything that's too crazy in here. Again, outliers, we're looking at -2, +2. Again, nothing too crazy is going on in there. Everything was between -1.5 and +1.5. So we're pretty set. All right, well, this actually ends our discussion of simple linear regression. In the next chapter, we're going to jump in, be talking about multiple linear regression. Really, I view these as an extension of each other. So these I don't really consider to be very different. I think multiple linear regression and simple linear regression are both just examples of regression. We just started small. So in the next chapter, look for us to do a lot of the same things, but start to expand slightly to incorporate multiple variables.